Hey, welcome back to Math with Patrick. Today is November 23rd, and we're solving problem 327 from the Daily Epsilon calendar. And here we have a system of equations with two variables, and I'll call this a symmetric system of equations, just because these equations that we're given are essentially the same. It doesn't really matter that this is r and that is s, because we could just swap the variables. And so essentially, the equations give us the same information. We do have this little note that r and s are not the same number. And then we're solving for x today. X should be 23, and it's the negative product of r and s. And I want to show a few things that failed for me first before I found a good solution for today. My first thought was it's a little bit hard for me to work with variables that I'm a little bit less used to. So I did think about just switching r to be x and s to be y. And so this was kind of my first thought here. And now when I see it like this, I'm a little bit more in like familiar territory where I could be like, oh yeah, why not? Let's just isolate y. So that'd be y is equal to x squared minus 24. We could isolate x. This is x equals y squared minus 24. And here I can clearly see a parabola whose y-intercept is at negative 24. And then thinking about this where like x and y is swapped, all I'm doing is essentially finding the inverse function of this. I guess technically it would be an inverse relation just because it doesn't follow the rules of a function. But we're basically going to rotate this parabola like this, or I guess maybe like that, because I might be mirrored. Anyways, we are rotating it around or about this line y equals x. That's just what happens whenever you swap x's and y's in equations. So we're going to get some kind of x-intercept over there, and then a parabola that reaches out this way. So just graphically, or even like drawing a sketch, really, I'm able to figure out that we're going to have four different solutions to this system of equations, at least the first two equations. Knowing that r and s are different values, I can't pick any values along the line y equals x. And so I'm left with two different solutions here. There could be this solution and this solution when I look at it graphically. I did try putting it into a graphing calculator, and it did give me decimal numbers. And so it's hard to say once you have decimal approximations, if you multiply them together, if you actually do truly get an integer or not. So just using Desmos wasn't enough for this problem. So next, I just tried to solve it with substitution. Using these two equations that I wrote, I figured that I could replace maybe the x value, this like x squared minus 24. I could replace that value of x with y squared minus 24. My other equation tells me that they're equal. So I have some equation that looks like this, and I could expand this square. We're going to get y to the fourth minus 48y squared plus 576 minus 24. This is still all equal to y. And usually when you're working with polynomials, it's best to set everything equal to 0. So I got 0 equals, and then basically everything else. I'm just subtracting this y to the other side, and then I'll simplify my constant term at the end. And the issue here, though, is that this is a degree 4 polynomial. It's a quartic, and these are pretty difficult to solve. So I didn't really want to go about solving this one, just because if I did, and there is a quartic formula, but it's ridiculous and honestly too complicated for me to want to use here. So when I saw that I had a quartic here, I knew that I could solve it, but that I didn't want to. Here's what finally worked. Basically, I'm going to start back from the beginning, and I'm going to try to use elimination strategies here. I'm going to subtract one equation from the other. I could use subtraction, so x squared minus y squared should be equal to, and then 24 plus y minus 24 plus x. Those 24s do cancel out, so I do get just y minus x. And then I could have also tried using addition instead. And so I would get x squared plus y squared is equal to x plus y plus 48. And here, my overall goal is just to get r times s, which I guess over here is x times y. And I don't need to actually solve for x and or rather r and s to solve this problem. As long as I can isolate the product of those two variables, I'll be okay. So let's take a look at this left equation here. On the left side, we have a difference of squares, so I could write that as x plus y times x minus y equals y minus x. And here's where it's important that I can say that r and s in my equations, x and y, are different. So I am allowed to divide both sides by this x minus y. If these values were equal, I would be dividing by 0 right now, and that's no good. But fortunately, I don't have to worry about that. X plus y is equal to this fraction. And if we factor out a negative sign from the numerator, it becomes a bit more clear that we just have the number -1. Again, I'm able to do this because x and y aren't the same number, so I'm not dividing by 0. So x plus y is equal to -1, and this is huge. I could actually use this, maybe isolate a variable first, and substitute it back into one of my original equations. I'll just do this first one. So x squared equals 24 plus y is just kind of from the problem statement. But if I isolate this y is equal to -1 minus x, I am able to replace this y that was here with just -1 minus x. And this is a quadratic, and quadratics are fairly easy to solve. Setting this equal to 0, I get x squared, and then plus x, and then minus 23 is equal to 0. And here's where we can pause for just a sec, because I could use the quadratic formula to solve down for two solutions, x is equal to something, x is equal to something else. And then we could try multiplying those values together. Or we could use an interesting feature about quadratics where the product of their roots is just this final number. And the sum of the roots also is this number right here, this coefficient +1. And the idea being, like, if we have, say, a quadratic that looks like this, we know that the roots would be 4 and 6. Multiplying it all out, we would get something that looks like this. And we can see that this ending number here, this constant value, is just these roots multiplied. Now, there is a little bit of a catch, though. So I just showed that basically we have two different x solutions. Maybe let's call them x1 and x2. And once we find them, we can multiply them together to get this number -23. However, these are both of our x solutions, and we don't yet know anything about y, or r and s from the original problem statement. However, remember how I said that this is a symmetric system of equations? That basically means that it doesn't really matter what I did to solve for r or s. I could have done those exact same steps just because the setup for both equations is exactly the same. So it's not that special that I solve for x down here. I could have done all of those steps, and I would have gotten instead like y1 equals something and y2 equals something else. And those also multiply to -23. Now we do know that x and y, or technically r and s, aren't the same value. However, both of them have the exact same solution set. We're going to have some solution here and some solution there, and this value and this value cannot be the same because x and y are different. So it's almost like we just have the same two values that we're choosing from, but one solution would be where we have the different values, and the other solution is where we also have different values. Like I can't choose this solution and that solution because, again, r and s aren't the same. So either way, once we solve our symmetric system of equations, we would either get this scenario or that scenario. And it's once we multiply them, it's identical to just multiplying the two solutions for x. So knowing that we actually needed the negative or the opposite of r times s, that kind of gets rid of this negative sign, and we do get 23. So that is one way to solve the problem. It's a little bit weird because I am relying on the logic of symmetric systems of equations. So I think we could actually pull this value and bring it over here and try something a little bit more concrete. Here, maybe let's think of this as x plus y squared, although this is not equal to that, right? Because when I do this, I will get a middle term of plus 2xy. So let me actually subtract a 2xy to make sure that this is still equal to that. I'm going to substitute the sum of x and y being -1 as just -1 right here, and then plus 48. And actually, I could do that on the left side of the equation as well. X plus y is just the number -1, so I'll replace it like that. Let's maybe simplify the right side, simplify the left side, and then, well, we're trying to solve for negative rs, in this case, negative xy. So my goal here is actually to isolate negative xy, not x, not y, not xy, but negative xy. To do that, I'll subtract 1 from both sides, so I will get a... Oh, wait, I already did that. Because, my bad. This is the number 1 right here, and then I was just kind of like one step ahead of myself, I guess. Hold on. This should have been a 47. Then subtracting both sides by 1, that turns into a 46. And then finally, I do just want to divide by positive 2, so I keep this negative xy on the left side, and then I get the 23 on the right. So that's another way to solve the problem. You don't need to kind of think through this logic of the fact that the y solutions are going to be the same as the x ones, but flipped. It's just a little bit easier, I think, to consult both of these equations and just find some really clever substitutions to solve down for x times y, or I guess r times s. So in any case, we don't really need to know what those two values are. We do have a quadratic equation right here, so if you wanted to, you could figure out those values for yourself. But I do have enough evidence to say that yes, once we multiply these values, we do get the number 23. So I think I'm all done. Thank you for watching, and I'll see you tomorrow. Bye.